So in this video, we just want to take a little bit of time to introduce three space. You are used to doing things in two dimensions in your mathematical careers up till this point. You've dealt with X and Y. You have very rarely, if ever, dealt with a third variable. So what we're going to be doing in this section is we're going to be looking at uh, adding a third axis to the way that we plot points. So we have the x-axis, you'll notice, is coming kind of out of the screen toward us in this direction. The y-axis is coming out of the screen toward us, working to the right. And then the z-axis just works straight up and down from that flat xy plane. You'll notice we do have a negative axis for x, a negative axis for y, and a negative axis for z. This is the typical convention that most textbooks, and I would guess teachers and professors are going to use for orienting the three space, orienting the coordinate system that involves three variables. One other thing I want to mention on this screen before we leave it, this is something that for those of you that do some work with magnetic fields, electric fields, and eventually we're going to talk about cross products ourselves within the next handful of videos, but they follow what's called a right-hand rule. What the right-hand rule involves is placing the fingers on your right hand along the positive x-axis, and if you curl the fingers on your right hand toward the positive y-axis, then your thumb is going to point the direction of the positive z-axis. Once again, fingers on the right hand along the positive x-axis, curl the fingers toward the positive y-axis, and then the thumb on your right hand is going to point in the direction of the positive z-axis. So whenever you plot points in space, what you're going to have is you're not going to have ordered pairs anymore. You're going to have what's known as an ordered triple. So the way that ordered triples work is exactly how ordered pairs work. You still have x listed first, you still have the y coordinate listed second, but then you've got this new inclusion of a z variable or a z coordinate within that list. So the way that we plot these, and you'll notice whenever I've drawn my three-dimensional coordinate system here, I didn't draw the negative portion of the x-axis, the y-axis, or the z-axis, and this is kind of clunky to do. It's not really that nice to plot something that's supposed to represent three dimensions on a two-dimensional whiteboard or on a two-dimensional piece of paper. So this is typically what's done whenever you're doing this by hand. What we're going to do to plot the point 1, 2, 3 is we're going to go 1 unit for the x coordinate. We're going to come out from that 1 unit along the x-axis, 2 units for the y, right? So I've gone out 2 units, and then I'm coming up out of that flat xy plane, 3 units on the z-axis. Here's one with some negative coordinates here, so we'll take a quick look at it. So if I plot the ordered triple, -1 for x, so I'm working backward 1 unit along the x-axis. I'm working outward positive 3 units along the y-axis, and then I'm going to work down 2 units from that. And you'll notice I've kind of included these little dashed lines that kind of indicate how I'm moving along these axes, outward and then eventually up and down for the z coordinates. So, plotting these on your own isn't that nice. There's definitely some software that you can find online that can plot these a little bit nicer than we can do by hand. For those of you that take a full-blown Calculus 3 course, you'll eventually graph in 3 dimensions. What we'll do in this video is we'll talk about one more issue, and that's how to find the distance between 2 points. Let's say we wanted to know what the distance between this point that we plotted here was and this point that's down here. It's not as easy as using the regular old distance formula because we have a third variable to worry about. We don't just have changes of x and y, we also have a change in z. So we'll take a little bit of time to talk about how to find that distance. To set up that discussion, we'll look at briefly what are called octants, right? So you're used to using the term quadrant. Those are the 4 pieces that the coordinate plane is cut up into. Well, when you include the z-axis, you have 8 octants. The first octant is where all the coordinates are positive. The thing that you see highlighted on this screen is that 3 space, and I even mentioned this whenever we were doing the plotting discussion a few seconds ago. 3 space is cut up into a lot of different planes. So if I have a z coordinate of 0, I'm going to be in what's called the xy plane. I'm not moving up or down off of this. If I have a y coordinate of 0, I'm not moving off of what's known as the xz plane. And if I have an x coordinate of 0, I'm not moving out of what's known as the YZ plane. We're going to use planes to our advantage when we have our distance formula discussion in a few seconds here. I mentioned a little bit about eventually some of you are going to do some graphing in 3-space. One of the significant things that you're going to look at when you get to that portion of your course when you're doing graphing is you're going to look at what sorts of equations involving x, y, and z are going to graph planes. We'll go ahead and take a look at a derivation for a three-dimensional distance formula. So what we would like to do by the end of this screen is have the distance from point 1 to point 2. So you see point 1 down here, not pinning down the x, the y, or the z coordinates specifically so that we can develop a general distance formula. That's the goal by the end of this screen. I have another point up here, point 2. Again, I'm not being specific with x2, y2, or z2. I'm just denoting that these coordinates are different than these coordinates down here. So what we want is we want to know that distance from this point to this point. So what is d? What is going to make this manageable for us is if we actually include a third point. So notice how this third point is arrived at. The x coordinate and the y coordinate of point 3 are the same as the x coordinate and the y coordinate of point 2. The only thing that's changed between point 2 and point 3 is the z coordinate. So these points, point 2 and point 3, are in the same plane relative to x and y. They don't have the same z coordinate, but relative to x and y, that they're keeping the same coordinates. This point right here is in the same plane relative to z as point 3 is, right? Point 1 and point 3 have the same z coordinate. So if you think about how we can determine, and you'll notice I've completed a right triangle here. If you think about how we can determine the length of side A and the length of side B, it should be pretty easy to figure out what this distance is just via the Pythagorean theorem. If we have a measure for this vertical dimension and we have a measure for this diagonal dimension here for B. So think about how you're going to find A. A should be the easiest of these to identify because the only thing that changes when we go from point 2 to point 3 is the z coordinate. So if I'm just looking for this change in z right here, I'm just going to take z2 minus z1. So hopefully it's pretty obvious where we get the length of side A on this right triangle from. For side B, we are going to have to do something a little bit more creative. We're actually going to have to apply the distance formula. Z has not changed. There's no change in the z coordinate. So using our familiar distance formula, the one that involves x's and y's, to find side B, I'm going to have to do the change in the x coordinate squared plus the change in the y coordinate squared, and then take the square root in order to find that distance for side B. So again, I can do that because the z coordinate has not changed. These are in the same plane, point P1 and P3, relative to the z variable. So we don't have to involve the z variable whenever we do a distance formula calculation to find the length of side B. So think about applying the Pythagorean theorem to the big triangle that you see here. The legs are A and B, so A squared plus B squared has got to equal D squared. Well, we know that A is just the change in those z coordinates from point 2 to point 3. So A is able to be replaced with z2 minus z1. B is this ugly expression right here, just a direct application of our familiar distance formula. Well, when we square B, I'm just left with these two components added together, right? What's under the root, right? Squaring this expression here is going to get rid of the root. If I'm trying to solve this for D, I'm going to just take a square root in order to isolate D and develop my three-dimensional distance formula. I did do some rearranging just kind of for convenience and to have this look like the way the formula is going to look on the next screen. These three pieces are added together here, so it doesn't matter which order I add them in, so I just added them in the order of alphabetical order, X first, Y next, and then Z at the end. So the nice thing about the three-dimensional distance formula is that it's literally just an extension of our two-dimensional distance formula. We have the components that we would notice for our regular old two-dimensional distance formula, and then we have the Z component added on at the end there. So that's kind of nice. Hopefully this derivation makes sense. To use this formula, it's really not a big deal in order to use it. It's just plug and chug. So if you call this x1, y1, and z1. You call this x2, y2, and z2. It's just a direct, plug into that formula, evaluate, and you've got your distance. So problems like this shouldn't be that difficult to do. In our next video, we'll have a discussion on how to define vectors in 3 space, and this distance formula that we just developed is going to help us find the magnitude of those vectors.